Welcome back. So this is the second video of week 8 talking about subroutine. Last time we did not cover the very last example in the slides, and I didn't explain page 19 and 20 in your slides. So in this video, I would like to introduce some more challenging example. So especially for using MIPS assembly code to deal with how to save certain variable or certain register value in the stack. So last time we have covered the basic requirement of writing a MIPS subroutine using MIPS assembly code. In this video, we will talk about how to write a subroutine when you have to use the stack to save certain variable or certain register value. So this is also related to your lab 4, the last question in your lab 4. So I will basically give you some general example, explain how we store variable or register value in the stack, and I also talk about, do a little bit demo of the lab 4 requirement, explain the lab 4 requirement, and give you a little bit example how to write the code required in lab 4. So let's first look at the basic definition for color callee. So the requirement, so page 19 and 20 in your slide 5, the requirement of using color and callee sub procedure. So the function calls other function is called a color. So the function being called by another function is called a callee. And sometimes the callee could be a color at the same time. And so they do not have a strict separate or division to divide the color from callee, callee from color. So the color and the callee, they have different responsibilities. They have different responsibilities. And we will first look at a figure. So as I draw last time, so we'll draw some figure again here. I think I'd better change the order of the note. So I told you I haven't talked about page 19 and page 20, so I will add 2 other pages here as the note. And then you can also, by the way, find the video lecture online, and at the same time you can find the slides with the video note. So there is another in the Blackboard lecture the slides folder, then you will be able to see all my notes. You will be able to see the PPT file, with the notes on it, So first of all, so when we have a caller and a callee, a sub function and a main function and a sub function, so we may have something like this, right? And then if you still remember, so we do have different conventions usage for the different register, So that's this page, right? So we call the S register, we call the S group, S register, as the callee saved register, and we call the T register as the caller saved register. What does that mean? So all the T group, including the T8 and the T9, including T8 and T9, they're called caller saved registers. And the S group, they're called callee saved temporaries or callee saved registers. So what does that mean? That basically means in MIPS assembly code, there is a convention that when you have the main routine, which we usually call it caller, and the subroutine, which we usually call callee, then they should use different group of registers. So the caller should use the $S register, could be S1, S2, any S register. So I will use SX here. And the callee should use the T registers. the callee should use the T registers. So this is by default accepted by everyone as a convention. Why we want to separate them? Because, for example, you might have them stored in different file, or you might have a really complex code. So you have your main function performing certain calculation, and the sub function performs some other calculation, and you really don't want to mess up the different job, the different task, right? So in a caller, then you might want to calculate certain task using the S register, and in the callee, you might want to perform some other calculation, use the T register. Suppose you can use totally different register, of course, then there will be no issue. There will be no issue. And then suppose I want to use the S register in a caller, and the callee also use the S register, then you might change the number, you might change the value of the register. And after you return back to the caller, then that may cause some problem, right? So I just want to give you a simple example, and then it will be easy to understand all the concepts. So first of all, suppose my caller is doing certain calculation with using the register T0, S0, using the register S0. And then what I did is, for example, ADDI $S0, I add $S0 by certain number, blah, blah, blah. And then later on, I want to have, subtraction using the $S0 again. And later on, I want to use $S0 for some other usage. For example, I will do LI $S0. So I'm kind of like using my $S0 all the time, because I assume $S0 is a container, is a variable, right? So I could keep changing this variable in my caller, in my main routine. And then what happens when you have a function call, then you will have a callee, you will have another subroutine. You will have another subroutine. So in your subroutine, you might want to perform some other calculation, which is totally not related with the caller, with the main routine. So for example, you might want to perform calculation A plus B is A minus C, all the other types, like some possible calculation. And in your calculation to implement A plus B, A minus C, then you might have to use the registers, because you do have a lot of temporary values. And what if I use the $S0 to store the value of A plus B, to $S0 to store the value of A minus C? So for any of the usage, then it will cause problem. Because if you use $S0 here, and before you make the function call, after you make the function call, so use $S0 all the time. However, you did not know that the register value of $S0 is actually changed in your subroutine, because when you look at the main routine, then you don't see what's happening in the subroutine. And then I will assume I will just use $S0 as euro. So I keep changing the $S0 value. However, when you jump to the subroutine, then it is actually being updated. It is actually being updated. So when you come back, then this value is not equivalent to the previous value. It's not equivalent to the previous value, because it is updated in the subroutine. Updated in the subroutine. So how can we avoid this kind of issue? Then of course, then we do follow certain conventions. So the callee should use the T registers, and the caller should use the S registers. And if that's the case, there won't be any problem caused by the previous example. Suppose if I want to calculate A plus B, A minus C, those type of regular calculation, then I can use the T registers to hold those values. Then it will not cause that kind of problem, right? So this is the convention. This is the convention of the caller and the callee. So the caller should use the S register. The callee should use the T register. So that's why we call the S register as callee saved, the T register as caller saved. So what did I mean by callee saved or caller saved? For example, so if callee has to use S register, so callee can always assume the T register belongs itself. And the caller could assume the S registers belongs to itself. But if the callee has has used all the T register and it's still not enough, so you have a really complex calculation in the callee. And even I used all the T containers, I still need a few more containers. So I have to borrow some S register. How about that kind of situation? So you have to use certain S register. You cannot rely on all the T register because you do need, for example, 20 containers, and all the T register can give you only 10 containers. So you have to use some other register, and then you have to borrow from the S group. So if I want to use any of the S register, then I have to save it somewhere. So it's kind of like if you have to use certain container, but that container could be used by other people, then how can you use that container? Then you have to store the original content of that container somewhere before you use it, right? And then where we can store it? In the stack. So the stack serves as the temporary storage, to keep a certain variable or register's value before you use them. And later on, you could restore the content of the register from the stack. So then how this example will change? So here we suppose then we have to use the S register. Suppose I have to use S0 and S0 in the main function, and I have to use S0 again in the sub function. So how it will look like? So my main routine is this line, and this is my subroutine. Right? So of course, this is called caller, and this is called callee. This is my sub function, and it is also called callee. So when I have the main routine and the subroutine, suppose $S0 is used here, and $S0 is also used after you finish the function call. And this line represents the function call. So you jump out from this point, and you come back to the same location, following that point again. So after you finish the subroutine. And then what's happening here is your subroutine is really complex. You have used all the T registers. They're all used, and then that's still not enough. So you have to use some other register. And how about suppose we have to use $S0. And before I use that, because I don't want to mess up what is being done in the caller, and I don't know what is the current value of S0. There's no way for the caller and the callee to communicate about everything, right? So when your callee try to finish the required task, the callee has no knowledge about what's the value of the S registers. So suppose you have to use the S register, then you have to save it. So that's why the S group, they're called the callee saved. They're called the callee saved register. That's why the S group, they're called callee saved register. And the T group, they're called caller saved register, because the T group belongs to the callee, and the S group belongs to the caller. So if the caller want to use the T register, then you should save it. If the callee want to use the S register, then you should save it. So let's look at this example. Suppose the callee has to use a certain S register, then I have to save it before I use it. And the only space I can save temporary values is in the stack. So remember how we use the stack. The stack is kind of like a queue. It's not a queue. So the stack is kind of like a memory growing from the top location to the bottom. And the SP is the register currently pointing to the top of the stack. And I would like to save the S0 into the stack. So as I told you before, so for example, if we view S0 as a container, and what is inside of S0 is the real content that I need to store in the stack. And after I finish my subroutine, I should restore the value of the S0. And when I return back to the main routine, then S0 will remain the same value as previous step. So I will not mess up. The value of S0 in the subroutine. So how can I save anything in the stack? Suppose the S0 is a container, and inside of the container there is an apple. So what I have to do is I need to put that apple into the stack at a certain location. And then I have to tell everybody that the stack first space is occupied. So the first space of the stack is occupied. By changing the SP value, so it was originally pointing to the top, then it will point to one space lower. Then anybody want to use the stack, then they could push the SP to lower location, but they will not mess up my apple. And later on, after I finish the usage, finish calculation of the whole subroutine, then I should restore the apple. So I first need to store S0's value, which is the apple, in the stack. So first I need to put $S0 into the stack. And the second step is finish my regular required calculation. So the task of the subroutine. So do whatever originally we want to do, and use S0 as a regular register. And the last step will be, well, I need to restore the value of S0, and I just need to take the apple out from the stack and put it back into S0. And then the very last thing will be I need to return to the main routine. So remember how we return to the main routine, we use JR$RA. And then when we come to the subroutine, then the A registers, they're already initialized. So I can perform whatever task, but I have to temporarily keep the S0's value in the stack, and then I will perform all the required tasks. And then I need to restore the value from the stack, and then I could return back. So how can I implement this in the code? Remember that we have to tell everyone about how the stack status. So if I want to store anything in the stack, there's generally a few steps. Originally, the stack pointer point to the top of the stack. And suppose I only need to store S0 in the stack, which requires 32 bits, because every register is 32 bits. And that will be 4 bytes. There will be 4 bytes in the stack. So the memory address of the stack pointer, and the stack pointer need to be pushed to a one word lower than original. So how can I tell everyone that I took one word from the stack by changing the stack pointer? So the very first step could be ADDI. Well, you can use subtraction, but ADDI is also fine. So I can change the stack pointer by -4, because I need to allocate 4 bytes in the stack. And then by doing that, then the stack pointer will point to this location, And then when I have the stack pointer point to this location, one word lower than before, then I could actually store my S0 into that location. So how can I put S0's content into this location? So I need to do store, right? So it's store word, and $S0 in which memory location? That will be SP0. $SP. So using $SP to point to this location, And after I finish, and the following part of this will be, so you have already stored your S0 into a safe location, and then you can use your S0 as the T register as whatever you want to do. So you can use the S0 as a regular register and perform whatever you want to do. So that's the required task of the subroutine. And then I could, after I finish the required task of the subroutine, which including update the V0 value, because you have to put the return value into V0, including update the V0 value. Then I have to restore the restore the S0's value from the stack. So I will just load it back to $S0 from the stack address using that address using the stack pointer. And after I restore the value from the stack, then I should tell everybody else, then I don't need this anymore, so you could take it. So I will move the stack pointer back again. So I first push the stack pointer down, and then I push the stack pointer, pull it up again. So the last step will be add the stack pointer by 4. The first step is subtract the stack pointer by -4, subtract it by 4, and the last step will be added by 4. So this is the general procedure of saving register value in the stack. So because the callee need to save the S registers if you want to use the S register, so we of course follow the same stack usage. If we want to use some T register in the caller procedure, because the caller should only use the S register, and if you want to use other T registers, then you should save it in a safe place. So that's exactly the same method we introduced here using the stack. And usually, if I have a usage of, for example, $T0 somewhere in the caller, and it's just for a temporary usage, so I mean, it's only like one step, two-step usage of the T0. So I don't need to worry about mess up the callee procedure, the sub procedure. So that's why, like in the previous labs, we never save the T registers because, of course, first of all, there's no subroutine before this lab. So there's no subroutine before lab 4, so we don't need to worry about the T register's value. And another situation, another reason is actually, so we use the T register to hold some temporary value, and we don't want to use it for like long term, like the S register, you use it for long term in the main routine. So you don't want to use T register to hold a certain value for long term. So you never want to worry about saving those values. However, a really popular usage for the stack is saving the S registers, because you might want to use the S register to hold some important variable value, and you keep using the variable value in the whole main routine, So you don't want to mess that up, so you have to save it in the subroutine. And a tricky thing will be, suppose I do not want to use it again. So for the S register, suppose I only use it here before I jump out, and I never need to use it again. So then you, of course, do not need to save it. You do not need to save it in the stack. And in your lab and any future test, so I will clearly tell you, well, you have to save the S register and you have to use S register in your subroutine. So then you will follow the stack usage. You will basically follow the stack usage. So certain compilers, they could optimize the whole process For example, certain compiler could check, oh, the S register is used here and it is used here again, so you have to store it in the stack in the subroutine. Or certain register compiler, they're not that smart, not that intelligent, so they may have to save all the S register as long as you use it in the subroutine. And certain registers, certain compilers, they can be really intelligent, so they do like the check, they do a real-time check that if I need to save the S register in the subroutine or not. So this is really depends on different compiler, different machine you use. So that's why in your future test or lab or any question requirement, then I will clearly tell you, suppose you want to use the S register in the subroutine and you want to save it in the stack. And if I ask you to save it in the stack, that means you may have possible long-term usage in the caller using the S register. So you have to save it in the subroutine. All right, so let's look at some the lab question, the last example in the slides, and then we'll also look at the required lab question. So the last example in the slides is like a really complex example, and I copied this technically from your textbook, so you could actually find it in the textbook with a little bit more explanations. So it is an example in the C code. So suppose you have a subroutine, and the subroutine is called G with two input variables X and Y. So the main routine need to call this subroutine. However, there's a troublesome issue of that subroutine is you do need to have, you do need a 32 integer array, 32 elements integer array in the subroutine, 32 integer array in the subroutine. So how we could implement this in the MIPS assembly code? You will never have such complex example in your lab or future exam, whatever, but I just want to give you a complex example, try to understand the convention of MIPS assembly code. So suppose I have a really huge array in the subroutine. So because I need 32 integers in the subroutine, which is impossible for me to put all of them in the T register, right? So if I use any of the register, then I mean, it's not enough. It's not enough. So I have to allocate a piece of really big memory space to store 32 different integer numbers. So I may have to use those numbers for different types of calculation inside of my subroutine. But the very first thing is where I can store where I can have those 32 integer number. If I have 32 integer numbers, there's no way for me to put all of them in the registers. So the very first thing is, well, we have to use the stack. So if I want to use the stacks to store the 32 integer numbers, so then I need to allocate certain space. And as the previous example I told you, so for me to use the stack, there's always a few steps. So the first step is always change SP, because I need to tell everybody how much space I need from the stack. So I need to actually decrease the SP. And then I could perform whatever task, whatever calculation required in the subroutine calculation task. And then I need to restore. And then the last step will be I need to restore the SP, to tell everyone that, oh, I have finished the usage of the stack. So for this particular example, there are 32 integer numbers I need to store in the stack. And one integer number basically requires a word. One integer number is 32 bits long. So that equals 4 bytes. So if I want to store 4 bytes in the stack, then I have to push SP by -4, decrease SP by -4. However, there's 32 of them. there are 32 of them. So I have to decrease SP by 32 times 4, which is 128. 128. So that's why I have ADDI. You don't have to use ADDI unsigned version. So you could do ADDI SP negative 128. You could do ADDI SP 100 negative 128. And whatever the dot here represent whatever the calculation task we want to do in the subroutine. So before we go to the last step, we have to pay attention that so the required task of your subroutine also include update your V0, because V0 will be the return value. So we get ready to return, right? So that's one step of the required calculation task. And before we return back to the main routine, using JR, we could return back to the main routine. Then we also don't forget that we also need to increase the SP by 128, because if you allocate 128 space, which is 32 integers, then you need to release those. You need to release those spaces. So the hot stack will look like the first, the SP point to the top point of the stack, and then you push it down by negative 128. So we basically change SP value to be SP minus 128. And then after we finish the calculation, then we go back again to the original SP value. So this is actually related to your lab 4 question, the last question of your lab 4. So in the last question of your lab 4, so I require you to perform certain calculation in your subroutine. So this is your subroutine. So in your subroutine, you have like a plus, a minus, so addition, subtraction, certain calculation. And I told you, well, the T1, T2, which are two variables in your C code. T1, T2 are the two variables in your C code. So they have to be stored in the S register. And if I have to use S register in the subroutine, then try to avoid mess up the possible usage of the S register in the main routine. Then I have to store them in the stack. So actually in this problem, then besides the general main routine, subroutine procedure, then you have to pay attention that the two variable T1 and T2 have to be stored in the stack, on the stack. So if you want to store something in the stack, then you have to, first of all, push SP, change SP to be lower value. And if you need to store two integers, then you need to do ADDI SP negative 8, because you want to subtract SP by negative by 8. You want to allocate two words. And then you could perform, you could store the current S0 value and the current S1 value. So if I want to give you a hint, then we could look at the, so let's look at the code later. So first I'll give you a brief explanation. So we first need to store the S0, current S0, and the S1 value, current S0 and S1's value on the stack location. And I need two different stack location, two different words in the stack. So I need to decrease the SP by 8, and put S0 on one word and put S1 on the other word. And then I could perform the general calculation required here. And then I need to change the restore the S0 and the S1 after I finish all the requirement in the subroutine. I need to restore the value from the stack. So take the value from the stack back, put it back into S0, put it back into S1. And the last step is change that stack pointer to the original location, So that's the complex part for the subroutine. That's the complex part for the subroutine. All right, so let's look at the requirement for the first, second, and third problem. So this lab basically asks you to get familiar with writing the subroutine. And as I told you, so if you want to use separate files, assembly files, to represent different function. For example, I could have a main function and I could have a sub function. So the sub function can be stored in a separate file, And then if they are in different file, then how can we compile both files together? So there we have to follow certain setting. So first of all, you need to declare the sub function as global. So you will see dot global. So the global directive, we should use globl. So this is the directive for global usage, global. So we could declare something as global by dot globl. So you have to put dot global before sub function. So you have to declare the sub function, declare this label to be global, visible to other files, because you do have sub function here in your main file. So this is assembly code, and this is another assembly file. This is one assembly file, this is another assembly file. So if you want this sub function to be able to understood by the compiler, then it has to be a global. Label. It has to be declared as a global label. So that's why I have to put dot global here. And then when you run this file, then the sub function label could be translated, because it is visible to every file. It is visible to the main file. So you could declare the main label to be global, but you don't have to do that. And by default, we could the main label is viewed as the entrance of the whole program. So when you have multiple files, file 1, file 2, then the main label is by default is the entrance location of all the files. So you don't have to declare it to be visible to every other file. And besides, you don't want to call the main function by another sub function. So usually we call the sub function inside of the main function, but you don't want to call the main function inside of a sub function, of course. So when you have this multiple file, suppose you want to use 2 separate files in the assembly code, then how can you run them together? How can you compile them together? So make sure the labels are declared to be global using the global directive. And also we need to check certain settings in the Mars simulator. So I gave you a figure here, helps you to, if you follow the direction here, instruction here, then you could have the proper setting. So we have to check assemble all files in the directory. And we have to check initialize program counter to the global main, That means, so this actually means the main label here, serve as the entrance of all the files. So you have to check those 2 settings. And because I check assemble all the files in the current directory, so I would suggest you to put the files in one folder. So for example, if I go to my assembly code folder, so lab 4 is a separate folder. So you want to first create a folder, you can name it as lab 4 or whatever. But later on, then when we run the code inside of that folder, so the current directory, so everything inside of this directory, inside of this folder will be compiled together, by checking this setting, So how can we do that? Suppose we want to run two separate files. So I want to show you a demo. So first of all, so I have two files open in my simulator, two files open in my simulator, and they are both of them are saved in this folder, So it's lab4a 3a, lab4 3b, lab4 3a, lab4 3b. So you want to make sure you put both of them under the same folder. And then I would like to change the setting here, because instead of compile each file, that's what we did before for the other labs, we want to compile both of them together. And when you look at both of them, so there is a main file, there is a main function here. And don't forget to put the exit. Here, because when you have subroutine, main routine, when your program become more and more complex, you do want to make sure you want to exit the whole process, and you always want to put an exit at the end. You'll always want to put an exit at the end of your main routine, to successfully terminate everything. And lab4 underscore 3b, this is my subroutine. So I have to have a subfunction label. So there is a label called subfunction, and then I want to declare this label to be global. So I could have certain data segment for this program, and I have certain data segment for my main program. So they could have separate data segment, because this piece of string is only used in the subroutine, and this piece of string and this piece of string, they are only used in the main routine. So I don't need to make this available or visible to every file. I only need to make the subfunction to be visible to all the other files, to be visible to the main routine. So if I want to compile both of the files together, then I have to check, first of all, initialize the program counter to the global main if defined. So that means your program will start from the main label, and I want to assemble all the files in the current directory, in the current folder, So check this as well. So check this and this, okay? And then let's try to assemble them. So when I assemble them, then you will see, wow, so this is not only the, let me see, JAL. Suppose I do it step by step. So we have two different files, then let's try to execute them all together. So I first checked the two different settings here, assemble all the files in the same folder, and initialize the program counter to start with the main label. And then I could just do assemble. And after you do assemble, then actually this includes this includes all the code inside both the main file and the sub function So the main file basically I want to print out two things. One is before sub function call, one is after sub function call. So I want to print out the before sub function call before I jump to the sub function. And then I want to print out the second string, want to print out the second string after I finish the sub function. And what does the sub function does? So the sub function only print out I am the sub function. So ideally, if you run them together, then we should print out before sub function call, and you go to the sub function, and then you should print I am the sub function. And then the third thing we print out will be after sub function call, So we should print out before and before sub function call, I am sub function call, and then after sub function call. So then let's look at the code. Suppose I execute this step by step. So first of all, I have some initialization in the main routine. And then when we go to JAL, so next instruction getting executed will be not this line after the JAL. It will jump to the subroutine. And finish whatever required in the subroutine step by step, and then go back. So when I have JR, so it will actually go back to the main routine after the JAL. So it will execute. After the JR is executed, then we will execute the line next to the JAL. And then a few more steps. We want to print out some other things, and then we want to exit the whole program. Because you do have a few jumps here, so I will suggest you always have an exit number 10 system call in your main routine. At the end of your main routine. If you don't have that, you may keep jumping back and forward and never be able to terminate the whole progress. So please include exit in your last line of the main function. So I want to do a more step, and then it's all done. So, and then when you look at the console output, you should have first before the function call, and second step is I am the function call, and the last one is after the function call, and then the program is finished. So this is an example, and that's the third question of your lab 4. So for lab 4, number 4, so the last problem of your lab 4, the first two problem is for you to practice and get familiar with the setting to compile different multiple files in one folder. And questions 3 and 4. So that's the real question. You need to submit your answer. And we did, we already finished the demo of number 3. So you should know how to do number 3. And number 4 actually asks you to, first of all, implement everything required here. And then you have to pay attention. I require you to store T0, T1, T2, those two variables using S register, So if you want to use S register, then you have to store them in the stack, because the S register could be possibly used in the main routine as well. No matter you use it or not in your program, you have to store it in the stack, okay? I want to make this clear. So not all the compilers could detect the usage of each register. So in our requirement here, I ask you to store it in the stack. So you have to do it. If you don't do it, then you will get 0 credit for this particular problem. So you have to store the variable T1, T2 in the stack before you use them. You have to store the T1, T2 in the S register, and you have to store the S register on the stack. So we basically need to perform addition and subtraction with the input variable X and Y. And remember, the subroutine always assume the input arguments, input parameters, they are stored in the A registers. And after finishing all the calculation, then we will need to put the return value in V0. The main routine is responsible to initialize all the A register, because that's the input variable. And then initialize another variable and put a number 0 in it, and then call the subroutine using JAL. And after the subroutine was finished, then I need to print out the value of z, So the z here is actually returned from the subroutine. So let's look at how to work on this problem step by step. So let's look at the last question in lab 4. So first close those two files, then open the last question, file 1 and file 2. By the way, you don't have to use two separate files in the last problem. I think I did require you to submit one file, to submit one single file for the last problem. So the problem 3 is trying to test if you could run two separate files altogether. And the last one, you could, of course, have two separate files. That's another way to implement this. But for this particular requirement, I require you to submit one single file, including the main routine and the subroutine. So you don't have to declare the subroutine, the label for the subroutine to be global. You don't have to do that because you could only you could submit one single file, including two labels, the main routine and the subroutine. So in the code I'm trying to show you here, so I do have the main routine and the subroutine together. So the requirement is I need to first initialize 3 different variables, x, y, and z, and then we need to make sure the x and the y, they serve as the input variable. They serve as the input variable of your sub function. So that's the arguments, that's the parameters we need to pass to the subroutine. So if they are the parameters, if they are the arguments, then we have to put them in A0 and A1. Have to put them in A0 and A1. And then we need to use a JAL to jump to the subroutine. So when you jump to the subroutine, then we only need to perform required calculation of the subroutine. So inside of the subroutine, we need to perform addition, subtraction, certain type of required calculation like addition and subtraction. And I require you to put the result of the addition, which is variable T1, into the register S0. And I also require you to put the result of the subtraction into another register S1. And if you're using S0 and S1, then you have to make sure they're temporarily stored in the stack before you use them, because you need to allocate 2 words in the stack. So we need to change the stack pointer by subtract it by 8. And then we need to put the S0 and the S1 into the 2 words we allocated. And later on, we need to restore them from the location we stored in the stack. We need to restore them from the stack. So you basically do the load and store from the same location. And the last step before you jump back to the main routine is add the stack pointer by 8 to move it to the original location, So this is a quick overview of the last problem. And I hope this could help you.